Hello, my name is Danija and I'm presenting Dream to Control, Learning Behaviors by Latent Imagination. This is joint work with Timothy Lillicrap from DeepMind, Jimmy Ba from the University of Toronto, and Mohammad Nourouzi from Google Brain. We present Dreamer, a scalable reinforcement learning agent that solves control tasks from pixels using a world model. To learn far-sighted behaviors, Dreamer learns an actor network and a value network from imagined sequences of compact model states. The actor is updated efficiently by backpropagating gradients through the multi-step predictions of the differentiable world model. Dreamer consists of three components that can be executed in parallel. From the dataset of past experience, it learns a world model. Using the world model, it learns behaviors in imagination using an actor network and a value network. The actor interacts with the environment to grow the dataset of experience. Let's look at these components in detail. To learn successful behaviors, we need to learn a world model that accurately predicts future rewards. To learn this world model, we draw a sequence of images, actions, and rewards from the dataset of past experience. The images are encoded using a convolutional network. Given the embedded images and actions, a recurrent neural network predicts a sequence of compact model states. These automatically learn to represent concepts that are helpful for predicting future outcomes. From each model state, we then predict the corresponding reward. We also reconstruct the image to facilitate representation learning. Predicting ahead using compact model states instead of raw images lets us efficiently predict thousands of sequences in parallel on a single GPU using a large batch size. Moreover, the compact model states learn features that facilitate accurate long-term prediction, as shown here for two environments. For 5 input images, we first visualize their reconstructions by the world model. Given future actions but no further images, we then use the world model to predict a sequence of future model states. For visualization, we reconstruct these states back into images, revealing accurate video predictions for 45 steps or more. Using the world model, we want to derive behaviors from it. We use 2 neural networks for this. An actor network is trained to predict successful actions. And to consider rewards beyond the prediction horizon, a value network estimates the expected future reward of each state. Here is how we learn the 2 networks. We start by encoding past images to obtain a set of initial model states. Using the actor network to select actions, we then predict a sequence of model states. For each model state, we predict the corresponding reward and value. To improve the actor, we backpropagate these rewards and values through the sequence of model states back into the actor network. To differentiate through stochastic states and actions, we use reparameterized samples or straight-through estimation. The value function optimizes Bellman consistency. That is, the value at each state is trained towards the reward plus the value at the next state. Having access to the world model, there's no need for Q-learning. These are some of the behaviors learned by Dreamer, given only images shown here as input. The top row shows a range of challenging control tasks with continuous actions. The bottom row shows visually more diverse tasks with discrete actions. These tasks pose a variety of challenges to the agent, including highly nonlinear dynamics, many underlying degrees of freedom, and 3D scenes. We empirically compare Dreamer to existing methods on a benchmark of 20 continuous control tasks with image inputs. The well-known A3C algorithm was trained for 100 million steps, or 23 days that would have passed inside the simulation. Planet, the state-of-the-art agent using a world model, surpassed this performance with 20 times less environment interaction. This corresponds to just over a day inside the simulation. With the same amount of environment interaction, Dreamer drastically outperforms both methods, achieving higher performance on all of the 20 tasks. Dreamer even exceeds the highest reported performance on this benchmark, that of the advanced D4PG agent, that was given 20 times the amount of environment interaction. In summary, Dreamer outperforms previous model-based and model-free methods in terms of final performance, data efficiency, and computation time. To find out more, check out our Google AI blog post. The blog post, a simple and efficient implementation to build upon, videos, and the paper can be found on the project website, danija.com/dreamer.